In this lesson, we'll talk about some terminology related to solutions, and we'll also review how to determine if a compound is polar or nonpolar or ionic. A solution is defined as a homogeneous mixture where one substance dissolves into another. It's made up of at least two parts. The main part is known as the solvent. This is the substance that does the dissolving. Now sometimes it's hard to determine this, so it's also defined as the substance that is present in the largest amount. What you dissolve into the solvent is known as the solute. An example would be making a copper sulfate solution, where we take copper sulfate solid as our solute, mixed into water as our solvent, and we would get a CuSO4 solution. Notice that there's no rearrangement of elements here. The solid just dissolves in the water, so we get the state change going to AQ. This means when you make a solution, it is not a chemical reaction. It's just a physical change. This can be reversed, separating the solute and solvent using a physical property like the boiling point. For example, you could boil the water solvent away and get your solid copper sulfate back. One misconception people have about the word solution is that it always is a solid dissolved in a liquid. Solutes and solvents can be in any state. You can have gases dissolved in gases, you can have gases dissolved in liquids, you can have solids dissolved in solids. Check out Table 8.1 on page 355 for some examples. Quantitatively, we can describe how much solute dissolves by describing the solubility. Solubility describes the maximum amount of solute that dissolves in a given quantity of solvent at a certain temperature. For example, the solubility of sodium chloride is 36 grams in 100 milliliters of water at 20 degrees Celsius. If a compound is soluble, then you can dissolve more than 1 gram in 100 mils. If it's insoluble, then it doesn't mean that none of it dissolves. It means that less than 0.1 of a gram dissolves in 100 mils of water. So anything that's insoluble on our solubility chart really just has an extremely low solubility. If a solute is somewhere in between 1 gram and 0.1 grams, it's described as being sparingly or slightly soluble. If you're adding solute to a solution and you add less than the solubility of the compound, the solution is known as an unsaturated solution. All of the solute will dissolve into the solvent and there will be extra room left over. If more solute is added, it will dissolve as well. Therefore, if you exceed the solubility of a solute, then you are creating what's known as a saturated solution. Not all of the solute that you added will dissolve in the water. It means that there's no more spaces left in the solvent, and some extra solid can be seen at the bottom of the beaker. Make sure you study and memorize all of these definitions. How a substance dissolves and creates solutions is affected by what type of compound it is, whether it's ionic, a polar molecular compound, or a nonpolar molecular compound. Before our next lesson, we need to review how to determine types of compounds. Here are 4 molecules. I want you to pause the video and draw the proper Lewis diagram of each of these chemicals. If you need to, Go back and review how to draw compounds and determine what type they are in your Unit 1 notes. After you've drawn the compounds, try to determine what type of bonds are present, what type of compound it is, and what intermolecular force it can make. Here are the answers. Here's the diagram for CH4, methane. Because carbon and hydrogen are both nonmetals, I draw circles showing the electrons being shared. Now the electronegativity difference between carbon and hydrogen is only 0.4, so CH4 contains nonpolar bonds. And therefore it is a nonpolar compound. Because it's nonpolar, it can only attract other molecules using London dispersion forces, which remember are the weakest intermolecular force molecules have. Here's the Lewis dot diagram for water. Remember, it should be a bent molecule. You need to follow the clock method when you're placing your electrons around the oxygen. Because oxygen and hydrogen are both nonmetals, I use circles to show covalent bonds. But oxygen is significantly more electronegative than hydrogen, therefore these bonds are polar, with oxygen being slightly negative and hydrogen being slightly positive. This compound contains polar bonds. It is also a polar molecule. I can separate the positive side from the negative side, or use the arrow or symmetry test to figure this out. In terms of intermolecular forces, because I have H's directly attached to O's, water can't hydrogen bond. Here's the Lewis dot diagram for CH3OH. We have two polar bonds here, the CO bond and the OH bond. Oxygen is stronger in both of them and receives a slightly negative charge. Remember again to use the clock method when you're placing electrons. It should be bent around this oxygen. We do this, remember, because lone pairs need extra room, so they're always going to be placed beside each other. This gives them more room in 3 dimensions, in front of the screen and behind the screen. This is also a polar compound. I can draw a line, my arrows don't cancel, and it's asymmetrical. I also have an H directly attached to an oxygen. That means this compound can also hydrogen bond. Here's the diagram for CH3Cl. Chlorine and carbon have a significant electronegativity difference, giving us a polar bond. This is also a polar compound. I can draw a line separating a positive and a negative side. My bond arrows don't cancel out, and it's an asymmetrical molecule. Because it's a polar compound and there's no O, N, or F connected to an H, this compound will dipole-dipole. There are some homework questions listed on the unit schedule. These are for practice. They are not for a unit assignment.